You are tuned to Iri-e-learning, and I am your host, Teacher. In this atomic structure lesson, we will be looking at isotopy. Check the description box for links to all the lessons related to this unit. By the end of this lesson, we should be able to define isotopy, list examples of isotopes, explain what is radioactive decay, and list the uses of radioactive isotopes, which include radiocarbon dating, diagnosing and treating diseases, research and industry generating energy, and tracing. What is isotopy? Isotopy occurs when an element exists in different atomic forms that have the same number of protons but different number of neutrons. These different atomic forms of the element are called isotopes. Therefore, isotopes are atoms of the same element which have the same number of protons but different number of neutrons. Now, there are three important things we want to keep in mind. 1. All elements have isotopes or different atomic forms. 2. Since the number of neutrons vary in the nuclei of the different isotopes of an element, then the mass number will be different for each isotope of the element. Remember, the mass number is the sum of the number of protons and neutrons found in the nucleus of the atom. Therefore, since the number of protons is the same for all the isotopes, but the number of neutrons differ, then this will result in the isotopes all having different mass numbers. And the third point, there are two types of isotopes. We have stable and unstable isotopes, and the unstable isotopes are radioactive. Stable isotopes do not change over time, while unstable or radioactive isotopes change into other forms or elements over time. When this change occurs, the isotope is said to decay. Let us take a quick look at the convention or format used for naming isotopes. The format used to name isotopes is rather simple. It's not rocket science at all. First, we have the name of the element, followed by a dash or a hyphen, then the mass number of the specific isotope. Using the three isotopes of carbon as an example, we'll see that the first isotope is written as carbon-12, and we read this simply as carbon-12. The same for carbon-13, we say carbon-13. Again, carbon-14, we say carbon-14. Keep in mind that 12, 13, and 14 represent the mass numbers of the specific carbon isotopes. We will now examine examples of isotopes for three elements. Don't forget that all elements exhibit isotopy, although we are limiting the examples to three elements. The first example are the isotopes of carbon. Carbon has three isotopes or atomic forms: carbon-12, carbon-13, and carbon-14. Carbon-12 and carbon-13 are stable isotopes, whereas carbon-14 is unstable or radioactive. Carbon-12 is the most abundant of the naturally occurring carbon isotopes. It has a relative abundance of 98.9%, while carbon-13 has a relative abundance of 1.1%, and carbon-14 exists in minuscule amounts, very small amounts. Take note that the mass numbers of the isotopes are different, but the atomic numbers are the same. Since all the isotopes of carbon have an atomic number of 6, this means that they have 6 protons each in their nucleus, because the atomic number is the number of protons. However, the number of neutrons differ. Remember, we calculate the number of neutrons by subtracting the atomic number from the mass number. As a result, carbon-12 has 6 neutrons. 6 from 12 gives us 6. Carbon-13 has 7 neutrons. 6 from 13 gives 7. And carbon-14 has 8 neutrons. 6 from 14 gives 8. Since the isotopes have the same number of protons, then they will have the same number of electrons, because the number of protons and the number of electrons are the same for any given atom. Therefore, each carbon isotope has 6 electrons. Consequently, the electron configuration for carbon is 2, 4. As we see here on each diagram, there are 2 electrons on the first shell and 4 electrons on the last or second shell. Since all the isotopes of carbon have 4 electrons on the outer shell, they all have similar chemical properties or behaviors. Next are isotopes of chlorine. Chlorine has about 24 isotopes with mass numbers that range from 28 to 52. However, chlorine 35 and chlorine 37 are the only two stable isotopes of the element. About 75% of naturally occurring chlorine is chlorine 35 and 25% is chlorine 37. As a result, the average mass number used on the periodic table for chlorine is 35.5, as we can see here on the periodic table. Scientists arrive at this value of 35.5 by finding the average of the naturally occurring chlorine using the following calculations. The abundance of chlorine 35 is 75%. Therefore, the scientists found 75% of the mass number of chlorine 35. 75% is written as 75 divided by 100. Then they multiplied by the mass number 35, and this gave 26.25. The same calculation was performed for chlorine 37, which has an abundance of 25%. 25% is written as 25 divided by 100, and then they multiplied by the mass number of chlorine 37, which of course is 37, and this gave 9.25. The average abundance of each isotope was added together and gave a total of 35.5, which is the average mass used for chlorine. Now back to the isotopes of chlorine. Notice that the mass numbers are different, but they have the same atomic number. Since the atomic number is 17, this indicates that both isotopes will have 17 protons in their nuclei. However, the number of neutrons differ. Chlorine 35 has 18 neutrons because the atomic number of 17 subtracted from the mass number of 35 gives 18. Chlorine 37, on the other hand, has 20 neutrons because 17 from 37 gives 20. Therefore, the nucleus of each isotope contains the same number of protons but different number of neutrons. Since the isotopes of chlorine all have 17 protons, then they will also have 17 electrons. Consequently, the electron configuration for each chlorine isotope is 287. That is, they all have 7 electrons on the last shell. Therefore, they all have similar chemical properties. And the third example is the isotopes of hydrogen. Hydrogen is the only element whose isotopes have unique names. Hydrogen 1 is called protium, hydrogen 2 deuterium, hydrogen 3 tritium. Hydrogen 1 makes up the vast majority of the naturally occurring element. Notice the 3 isotopes have different mass numbers but the same atomic number. Since each isotope of hydrogen has an atomic number of 1, then each isotope carries 1 proton in its nucleus. However, the number of neutrons differ. Protium has no neutrons. Subtract the atomic number 1 from the mass number 1 gives 0 neutrons. Deuterium has 1 neutron. Subtract the atomic number 1 from the mass number 2, which gives 1 neutron. Tritium has 2 neutrons. Subtract the atomic number 1 from mass number 3, and that gives us 2 neutrons. Once again, we see that the number of protons are always the same for isotopes of the same element, but differ in the number of neutrons. Additionally, the number of protons and electrons are equal for an atom. Therefore, the isotopes will have the same number of electrons. So they each have 1 proton, so therefore they will have 1 electron. All the isotopes of hydrogen have 1 electron, hence the electron configuration is 1. The diagrams of the hydrogen isotopes show 1 electron on a single shell, which is the outer shell. Therefore, the isotopes of hydrogen have the same chemical properties. Earlier, we mentioned that some isotopes of elements are unstable, meaning they are radioactive. We will briefly explain what radioactivity is and state the uses of some radioisotopes. What is radioactivity? Radioactivity, also referred to as radioactive decay, occurs when an unstable atom changes by emitting particles or fragments of particles and electromagnetic rays from the nucleus.
Note, the instability of a nucleus results either from having excess protons or neutrons. So the atom regains stability by ejecting protons or neutrons or fragments of these particles, depending on which is in excess, or by releasing energy in other forms. Here we'll take a brief look at some of the fragments emitted during radioactive decay or radioactivity. First, we have neutrons. Now, the release of neutrons is a very rare occurrence, but it is essential for nuclear power. Alpha particles, Greek letter represented here for alpha, is actually a bundle of 2 neutrons and 2 protons. Then we have beta particles. This is the Greek letter for beta, and beta are electrons, and electrons are actually a fragment particle that is released when a neutron breaks down into an electron and a proton. Gamma rays, and these are the other forms of energy, and they are electromagnetic rays such as X-rays. Uses of radioactive isotopes. Carbon-14. Carbon-14 is commonly used for carbon dating, also called radiocarbon dating. Now, how does that work? All living things contain a certain amount of carbon-14 while living. However, when living things die, the carbon-14 begins to decay or change over thousands of years. The age of the fossil or archaeological find is determined by comparing the levels of carbon-14 in the fossil to what it would have been if living. Carbon-14 is also used as tracers in research and medicine. Carbon-14 can be used to trace the steps involved in plant photosynthesis and metabolic changes for patients with anemia, diabetes, and gout. Tritium is used as a tracer for biochemical and academic research such as animal metabolism studies and groundwater transport measurements. Tritium, when mixed with phosphor, is used to make glow-in-the-dark lights, which are commonly used as luminous light sources for safety signs. Cobalt-60 is used in medicine, in radiation therapy, in the treatment of certain cancers. It is also used in the food industry for the sterilization of dry foods. And interestingly, it can also be used in the sterilization of medical instruments. Cobalt-60 is also used to monitor the thickness of materials and detect flaws in welding seams. Iodine-131 is used to monitor and treat goiter and other thyroid problems such as thyroid cancer. Also, it is used in the treatment of liver and brain tumors. Thallium-201 is used to diagnose coronary artery disease and parathyroid hyperactivity. Sodium-24 functions as a tracer in the circulatory system to detect obstructions. Uranium-235 is a nuclear fuel because a large amount of energy is released when the nucleus is split using a high-speed neutron. This process is called nuclear fission. The nuclear fuel, which is uranium-235, can be used to generate electricity, power nuclear reactors that run the propulsion system on naval ships and submarines, and make nuclear bombs. Now, isotopes such as plutonium-238 were once used to power heart pacemakers. The use of nuclear heart pacemakers came to a halt just about the mid-1980s as lithium-powered pacemakers took over the market, and these were deemed safer. So what have we learned from this lesson? Let's do a quick lesson summary. First, all elements exhibit isotopy. Isotopes of an element have the same number of protons but different number of neutrons. Radioactivity occurs when unstable atoms emit particles and electromagnetic waves from the nucleus, and radioisotopes are used in research, medicine, and industry. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. Identify the statement that is correct about isotopes. A. Isotopes of an element have the same number of protons and neutrons. B. Isotopes of an element have the same number of neutrons and electrons. C. Isotopes of an element have the same number of protons but different number of electrons. D. Isotopes of an element have the same number of protons but different number of neutrons. And the answer is D. Isotopes of an element have the same number of protons but different number of neutrons. Question 2. Which isotope would be used for dating ancient relics? A. Carbon-12, B. Carbon-14, C. Hydrogen-1, D. Chlorine-35. The answer is B, carbon-14. Question 3. All of the following are uses of the isotope cobalt-60 except A, irradiating food as a sterilization process, B, detecting of flaws in welding seams, C, generating electricity, D, radiotherapy for treating some kinds of cancers. The answer is C, generating electricity. Question 4. Which statement is incorrect about an unstable isotope? A, an unstable isotope is not radioactive. B, an unstable isotope displays radioactivity. C, the nucleus of an unstable isotope emits nucleon particles and electromagnetic waves. D, an unstable isotope has equal number of protons and electrons. And the answer is A, an unstable isotope is not radioactive. So that is the incorrect statement about unstable isotopes. Question 5. Which isotope listed below is a nuclear fuel? A, hydrogen-3, B, uranium-235, C, thallium-201, D, iodine-131. The answer is B, uranium-235. We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.